Um, it's getting warmer, right? Weather becoming warmer. And today we will study advanced DQ network. So in previous time we recap Q learning, DQ learning, and there were some tricky stuff and limitations in DQ network. So today we will study how can we address such kind of some tricky stuff in DQ learning. So first one is stabilization technique for deep Q learning, and the second one is addressing overestimation in Q learning. So this shows some kind of summarization of previous time, right? We learned replay buffer and epsilon greedy approach to learn optimal Q function, right? So the first we get this kind of data by taking one step with sampled action from policy network. This kind of policy network can be from our Q network, deep Q network, and then we can evaluate the target Y, target of our Q function, which can be computed by with predefined reward function, which takes state and action, and then we use gamma times maximal Q function. So here's the tricky one is that target is from our own network. That was the tricky thing. And we update theta using minimizing this kind of loss function, and this is gradient. So this is how we perform Q learning. And we store this kind of sampled transition state and updated state with action. We store such kind of data in our replay buffer, and then we use such kind of batch from buffer to update theta, right? To update theta, we sample batch from our replay buffer and then minimize this loss function to update theta. And this shows the epsilon greedy approach, so that with some probability 1 minus epsilon, we take greedy approach. We have some trained Q network, right? We have some learned Q network, so that we can take some action which maximizes Q value, right? That can be one way to sample action. The other approach is just random action. Remaining probability, we can just perform take sample random action. That can be our policy distribution, action distribution, used to sample action, right? And so here, as I introduced in previous time, the target Y is obtained by this one, and then it seems like a typical gradient descent, right? But Q learning is actually not gradient descent, because the target is also from theta, but this target we detach from the computational graph. So no gradient is backpropagate through the target value. So that makes Q learning is not gradient descent, because in gradient descent, all the parameters, all the functions parameterized with theta should be updated. But here, no gradient is backpropagate to the target value to stabilize the training, so that the Q learning is actually not gradient descent. So this shows the typical Q learning. We sample transition from our, we get this kind of transition from our sampled action, and then the difference, the important thing is that with each gradient descent, without some special treatment, target is moving, right? Because target is from Q theta, right? So that target can move. Although we detach, target is always moving, so that can make training quite unstable. Here, this shows how we update theta, and then here is target, which is also from theta, so that it makes training quite unstable. So that to address this, we actually I introduced this in previous time. This is called full faded Q iteration algorithm. The first and second steps are the same. We just collect data using some policy. It seems a little bit ambiguous, but we can just use our training Q function as a some policy. We can use such kind of our training function Q function as a some policy or some off-the-shelf policy function. Anything you can use. So that means we try to collect some data using some policy, including our learning Q function. And then here the difference is that here we have theta bar, right? So target is from not theta, it is from theta bar, which is different from theta. And then the third step is the same. We can just update theta by minimizing this loss function. But the important thing is that target is not from theta, but from theta bar. So here, theta bar. This is the current one, and this is the target. So important thing is that it is not from theta, but from theta bar, which is different from theta, so that it can address moving target problem, so that it can be, seen like a perfectly well-defined stable regression. We will study this in detail. So the difference is, as I said, target is not from its own network. Target is from some different network. So there can be several kind of different network, which is parameterized theta bar. I'll introduce later. So the thing that I introduced in previous time is using network from previous checkpoint, right? Targets here, the theta bar, only changes every 10,000 steps. So theta bar is from previous checkpoint of our learning Q network theta. So these are the same, just we get some transition from sampled action, and then we store this kind of transition to replay buffer, and then we sample batch from buffer. But here difference is that Q theta, we obtain target from Q theta, not theta. And we update theta using this loss function where y is from Q theta bar. And here theta bar is defined as the previous checkpoint of theta. So every 10,000 steps or so, we overwrite or we update theta bar with theta. So this can address some limitations, some tricky stuff of moving target problem, right? Because the theta bar for 10,000 steps, theta bar target is the same. Target is fixed. The target is not moving for 10,000 steps. Of course, after 10,000 steps, target changes, but for next 10,000 steps, target is fixed, not moving, so that we can make training a little bit more stable. The target is not moving, target is fixed. So there are pros and cons of this kind of target network. Target network means some dedicated network, some different network that is only used for getting targets of our Q network. So the good point is that it can make training stable, as I said. Stable optimization solves the moving target problem by keeping the target Y fixed for a period, making it a well-defined regression task. And prevents divergence, breaks the harmful correlation between current Q values and the targets, reducing the risk of the network oscillating or chasing its own noise. Yes. So we can reduce risk of the network oscillating or chasing its own noise. That makes sense, right? If target is always from itself, then target is always moving. Whenever we update theta, so that network will lose the path and it may chase its own noise. So that we can, by defining some fixed target network, we can address this kind of things, and then we can make training more stable. But of course, there's some bad things. The first one is slow value propagation. The training can be slower because the better knowledge in the theta is not immediately reflected in the targets until the next update. So we always update theta, but here we always update theta. The third step, we always update theta for each step, but we update theta bar with every 10,000 steps. So if this number, let's say this number is denoted by n, if n is too large, then theta bar might have some outdated knowledge, right? it might have some noisy or outdated knowledge, so that although our theta has some better knowledge, this kind of outdated knowledge might make training slower. That is the first bad thing, slow value propagation. Our Q function has trained enough, but still Q theta bar is too outdated, so that the knowledge that is included in our Q theta is not actually propagated to our Q theta bar. So the training can be slower, although it can be more stable. That is the bad thing. And another bad thing is the outdated target. It's a similar thing. For up to 10,000 steps, the agent might be learning from old and potentially inaccurate value estimates, leading to temporarily suboptimal updates, right? So in summary, good point is that training becomes stable, and training makes sense. Without this kind of dedicated target network, it actually does not make sense, and training will never converge. But by introducing this kind of dedicated target network, fixed dedicated target network, we can make training feasible and stable, but at the same time, it becomes slower than optimal setting. So that is the good point, the bad thing of these dedicated target networks. and we can actually generalize Q learning with replete buffer and target network. So this one, the below one, is the classic deep Q learning algorithm that we've learned so far. Let's see this classic one first. Classic one. Take some actions, A, and observe the state transition added to replay buffer, and sample mini batch transition from replay buffer uniformly, and compute target. Here we have target network Q theta bar, right? So we have target, and then we update theta by minimizing this loss function, and update theta bar. Copy theta every n steps. So in previous slide, n was 10,000 or so. So that was the deep Q learning algorithm that we've learned so far. But we can actually have more generalized view of deep Q learning algorithm. That is the above one. So the generalized Q learning with replay buffer and target network. We save target network parameter. We can override theta. We can update theta bar with the theta, and then we can collect data set using some policy added to replay buffer. As I said, some policy include our this kind of taking action, observe, taking action, and saving the transition to replay buffer. We can use our own Q network, or we can use some off-the-shelf policy network. We can use anything that is to keep some data, and then we can add it to replay buffer. And then we sample a batch from buffer, and then we update theta, and that is the same. I mean, this fourth step and this fourth step is actually the same. The important thing is that this is our output, and this shows target. Important thing is the target is from different network, theta bar. So the fourth step is the same, but here we have some difference one. So n is actually the same. In fifth step of the classic one, we also update theta bar with every n steps. So n is the same, but the problem is the k. We'd like to update our theta with a sample batch from the replay buffer, and we can perform the update only once, right? We can update once or several times. That is called denoted by k, and it's called update to date, UTD ratio. Using this kind of, if we increase k, then we can make training faster, of course, right? Because we can sample multiple batches from a replay buffer, and then we can update theta multiple times, so that we can make training faster. Usually k is decided in a range of 4 to 8. Self-directed creative. We will learn this after midterm. We'll learn all this kind of recent RL and robotic ISAC after midterm. And this kind of thing, set k is in the range of 20 to 40. So that is called UTD, update to date ratio. And the classic deep Q learning algorithm is a special case of the generalized Q learning algorithm where k equals to 1. So that it updates theta only once. But to make training faster, we can set k like in a range of 4 to 8 so that we can make training faster. And this shows the visualization of some limitation of the classic DQ network. So the blue one shows the first one, take action. This is blue one. Blue. Take some action and observe the transition and edit replay buffer. We always have this kind of data, and we save it to replay buffer. And we get target here. Let's say we target from here, theta bar. Here, theta bar equals to theta here. And we proceeded, because let's say n is equals to like 4, maybe 4 or 5. Then at here, there's no lag. Lag means some time difference. So that here there's no lag. But as we proceed training, as we fix the target network, as we fix the Q theta bar, and then we update theta bar for every n step, so that theta bar is fixed at the old time step, although theta is updated. So here, maximal lag. So theta bar is at this checkpoint. Here, theta bar is at this checkpoint, but here, theta is at here. So after many update iterations, so that there is a maximal lag, maximal time difference between theta bar and theta. And here, we again update theta bar with theta. There's no lag here. We repeat this one, so, right? As I said, so this kind of thing can make training feasible and stable, but at the same time, it makes training slower. So some alternative way to address this kind of thing. Alternative means like some solution for this problem. Solution for this problem is a popular solution is Paulic averaging. So we update theta, including theta and linear interpolation between theta bar and theta. Your tau is equals to 0.999 works well. What does this mean? So here, instead of updating theta bar for every n step, we update theta bar for every step. Here n might be equals to 1, n equals to 1. So majority of the contribution factor is from theta bar because the tau is equals to 0.999. So majority of the contribution factor is from theta bar. So it mostly tries to preserve theta bar that it used to have. But there is some kind of small new stuff from here. It tries to absorb some updated knowledge from theta while it tries to preserve majority of the stuff, right? Because tau is set to 0.999. That is Paulic averaging. So that is actually a popular alternative. It tries to, so that in this way we can some kind of address the limitation of introducing dedicated Q theta bar. By introducing Q theta bar, the training becomes stable but at the same time slower. The reason why it becomes slower is that it has outdated knowledge, right? Theta bar is at here, but theta is at here. So there is a big time difference between them at the maximal lag time step. But for every step, we try to preserve theta bar's knowledge while tries to slightly include newly updated knowledge from theta by setting tau equals to 0.999. This is Paulic averaging. So far good, no problem. And so we actually learned a couple of Q learning network, and let's summarize and make it clear what are difference between them. So that is general view of generalized Q learning with replay buffer and target network. we save target parameter theta bar with theta and collect and edit replay buffer, and then we can update theta with k iterations. And there are a couple of things, like a process one is data collection, which is the second step, this one, right? Data collection. And then process two, target update. Target update is from this one, target update, right? And process three is Q function regression, is from here, right? Evict means discard, remove. So we remove all data in our replay buffer. So there are, three processes in our general view of Q learning. The first one is we try to collect data using our replay buffer from our own Q learning network or some off-the-shelf Q learning network in any way, or just a random action, anything. We just try to collect some data set, right? We take action, we have initial state, we have some action from random action or epsilon greedy action, anything, and then we have updated state. So we try to collect some data and store it to our replay buffer. That becomes our training set. And then we have dedicated target parameter for getting target of our Q learning function that is denoted by theta bar, which is different from theta. And we update target for every n step to address the moving target problem. And process three is we try to update our theta, current parameter, where target is from theta bar. So DQ network, classic DQ network is a case where n is equals to 1 and k equals to 1. So every step we update the target network, and every step we only update our theta only once. That is a classic DQ network. So here we learn a couple of algorithms. Online Q learning, evict all data immediately. Process 1, 2, and process 3 all run at the same speed. That is called online Q learning. So online means it tries to collect data at the same time. It just uses the data to train the network. So online means, it does not do something in advance. If you do something in advance, that is often called offline algorithm. If you do something before you do something, then that is called offline algorithm. But if you do something at the same time, you do something A, and at the same time you do something B at the same time, then that is often called online algorithm. But offline algorithm, if you do something A before algorithm something B, the stage is completely separated, then the algorithm is often called offline algorithm. So online Q learning, it collect data, and then it just use that data to train our Q learning network. That is called online Q learning. So evict immediately, process 1, 2, and process 3 all runs at the same speed. That is called online Q learning. How about this one? Deep Q network, process 1 and process 3. Collection and this update Q function at the same time. But process 2 is slow. If we set n equals to, n larger than 1, then we update target slowly, right? We do not update target every step if n equals to 1. Sorry. If n equals to 1, then process 2 is slow. But if k equals to 1, then we just we collect data, and then we just use that data. So the speed of process 1 and process 3 are the same. And fitted Q iteration. Process 3, fitted Q iteration can be seen like a generalized Q learning, like this one. Fitted Q, we actually learned fitted Q, where is it? Here, fitted Q iteration algorithm. You can consider this a generalized formulation of Q network. Fitted Q iteration process 3, here, process 3, in the inner level process 2, and then within the inner level process 1, right? So we have 2 inner loops, right? The first one is N, which tries to update target network, and the most inner loop is updating our current parameter theta. So there is a N and K, so 2 inner loops. We have 2 inner loops. That is called fitted Q iteration. So we learn a couple of Q learning algorithms. Any chess difference one? Of course, apparently fitted Q iteration is the most stable one and most generalized form, and it might be performs the best, I guess. And as I introduced, so K is often called update to date ratio, UTD ratio. So we will study how K affects the training schedule. So higher UTD, it makes training faster, of course, right? If we increase K, then we give more chance to update our Q learning network theta, right? If K increase, then with the same target network, we try to update our theta more, right? So that makes our training faster. But if we set K too high, then it might suffer from overfitting. Because given replay buffer, that means the target is fixed, and the target is fixed because theta bar is fixed in this inner loop. So that the network can be overfitted to this theta bar, right? If K is too high, then network might be from the same batch, and the Q theta bar is also a fixed network, so that our Q theta can be just overfitted to this replay buffer and Q theta bar. So if K is reasonable range, then it makes training faster. But the problem is if we set K too high, then it might suffer from overfitting. So there is a answer. What happens with decreased N? So N is here, right? N is here. What happens with decreased N? Faster value propagation. So actually we learned this in previous slide by introducing some dedicated target network. We make training stable, but at the same time, training becomes slower. But what if we decrease N? Extreme case might be N equals to 1. If we decrease N, the faster value propagation. Q values propagate through state action space more quickly because target networks stay close to the current, more knowledgeable network theta, right? I mean, decreased N is like extreme case is N equals to 1. Then in an extreme case, theta bar is always the same as the theta. Then theta bar has always has updated knowledge, so that the learned value from our Q theta is easily included in our target network, Q theta bar. But this is a good point, but these are bad point. Increased risk of instability. Decreasing N brings us closer to the moving target problem, right? Which can cause the learning process to fluctuate, oscillate, and even diverge. And higher correlation. The correlation between current Q function and the target increases, which can lead to self-reinforcing biases and overestimation, right? Self-reinforcing bias. It tries to estimate its own noise that makes training quite unstable, oscillating, right? So we need some reasonable range of N. So such kind of stuff, we do not have to take care of such kind of stuff in supervised learning. Supervised learning, as we assume we have data, and most of the competition graph are differentiable, so we do not have to take care about this one. The target is always from data set, but on RL, we do not have targets in our data set, so that we actually try to make targets from our own network with some tricky stuff, using separated, dedicated target network or any other things. So that there are some tricky things. Training can collapse and becomes quite unstable easily, Then you need to take care about this one. In assignment 1, you need to also take care about this one. The training could be very unstable, although the assignment 1 is not very difficult one, so that without special treatment, the training can be successfully finished. But in many cases, this kind of Q learning and RL becomes quite unstable. And end-step returns. So that is something different. So here we have classic deep learning algorithm. These are the things that we've studied so far. And end-step returns, it tries to compute y in a different way. So the thing is that, so this one, you can see this figure. So this one, S is state, start state, and +1 is reward. So from start state, how can we make our agent know that going right is beneficial? To make our agent know going right is beneficial, then the Q function needs to be filled for every steps, right? But the classical DQ learning algorithm, it tries to fill numbers for, if we fill this number, then we can fill this one, fill this one, fill this one. So we need many steps to propagate this knowledge. Going right is beneficial to the start state. So that makes training a little bit slow. So that people invented a way to address this kind of slow training problem by introducing end-step returns. The only difference is in the third step, when computing the y. So here's the new way to get target y. This is the same. This is just the gamma and max and q theta bar, and then we just get maximal q function reaction is sample. That is the same one, but the difference is that this one, we introduce additional t prime, right? T prime is not included this one. There is no t prime. In the right side, there is no t prime, but here we have t prime in here. So let's say we have, when taking here, in the first step, when saving our transition data to our replay buffer, we only take action only once, right? We only take some action only once, and then we have initial state and action at that time, an updated state, and then store that transition to our replay buffer. But instead of taking action only once in the first step, we can take action several steps, right? Like, for example, n steps here, n step. We can take action n steps. Then we might have more transition data, right? So for example, S0, A0, S1, A1, S2, A2, S3, A3, right? So in original classic deep learning algorithm, we only save this one to our replay buffer. But if we take action 3 times, then we have longer data, and then we can save this one to our replay buffer, right? And each action can be sampled from greedy approach or random action. You can use anything. So in this way, we can save our data with longer sequence, right? And then we can use such kind of data to get actual reward, right? And then this one is just from our network. That's the remaining thing is the same. But from longer sequence of training data, we can compute reward from longer sequence, so that this knowledge going right is beneficial can be more quickly propagated to our start state, so that we can make training faster. That is the philosophy of n-step returns. Instead of taking action only once, that is the classic deep learning algorithm, we take actions n step, where n is of course bigger than 1, and then we can make training data transition longer, and then such kind of thing can be included when getting target of our Q learning algorithm, and then you can make training faster. So here is a comparison between classic DQ network and n-step returns. So classic DQ network, 1 step, update the Q value using only intermediate reward, and next state estimate leading to slow value propagation. That is, 1 step is also a special case of n-step returns. But n-step returns, how about this one? It accelerates learning by summing reward over n consecutive steps. before adding the bootstrap the future value, enabling much faster reward signal propagation, right? With nothing very special, but just we can take actions multiple times so that we can enrich our training set with longer sequences, and then we can compute our target with longer reward, so that the knowledge, which is very far from the start state, can be quickly propagate to the state, so that this kind of the iteration to get optimal Q function can be decreased. So that is the philosophy of n-step returns. So we can make lots of variations in classic DQ learning algorithm, right? There are actually many variants. Here, the making variants, the first step is n-step returns. Of course, the first one is introducing dedicated target network. That is the thing that we've learned the first time. That is the first variance that we can make. And another one is we can introduce, and this one, we can update theta bar with every n step. That is also some variance that we can make. And then this one, fourth step, by introducing k. So here n, here k. We can introduce k to update our theta not only once, but we can update theta many times. That is also some variance that we can make. And another one is n-step returns, right? Instead of taking action only once, we can take action multiple times so that we can compute reward for a longer sequence, which can make training faster. So there are several variants in our classic DQ learning algorithm. So why is it good? So faster convergence. So propagate reward information much more quickly across the state space, reducing number of episodes needed to learn. And lower bias relies more on actual observed reward rather than potentially inaccurate early stage Q value estimates. So this one is straightforward, right? But how about this one? It relies more on actual observed reward. What does this mean? So this means is that here the R are from reward, actual R from our predefined reward function. These are not from our Q network. These are not from any estimate. These are actual reward, right? These are actual reward. We have from this data, from this training data, we can compute reward for all pairs of state and action, so that we can prepare reward for actual data, right? So that we can rely more on this one. So original one, we only have reward for only one time step, but here for n step, we can have this kind of actual reward more than one step, so that it relies more on actual observed reward rather than potentially inaccurate early stage Q value estimate. That is the good one. There's always pros and cons, but the bad thing is that higher variance, cumulative reward over n steps are more sensitive to environmental noise than stochastic, right? That also makes sense, because especially in the early training stage, the Q function might fill up garbage values, so that the taken action can be very stochastic, so that the transition from state 0 to state 1, state 1 to state 2, state 2 to state 3 might not make sense, maybe. They might be not optimal, because the chosen action might be very stochastic. And off-policy mismatch. It is mathematically tricky to use with the replay buffer, because the n-step trajectory must match the current policy to be strictly correct. So this one is the thing that I've just mentioned before. So in the first step, we take action several times, but this transition from state 0 to state 1, state 1 to state 3, state 2 to state 2 to state 3 might not be optimal transition, because our action is not optimal, right? So such kind of data transition might not match the optimal one, so that they can introduce some problem, so that here the hyperparameter is n, right? N step here, n, right? You need to make a balance between this kind of pros and cons by adjusting n hyperparameter. If n is too high, and it might suffer from these limitations. If n is too small, then it might not enjoy these good things. You need to make a balance between this kind of good and bad thing based on your experimental result or some literature study, right? So there are many things you need to decide when you start reinforcement learning with your agent. So far good? No problem? And let's see the overestimation. So we so far learned the Q learning, and then, but how can we evaluate the Q values? Actually, we cannot, because we do not know ground truth. Of course, in some simple environment, we can pre-compute all the optimal Q functions with enough iteration, and then we can make evaluation. But for complicated environment, actually, it is almost impossible to evaluate this one. But in simple environment, you can see that this orange line, this orange noisy line is a DQ network estimate, and the orange solid line is a DQ true value. So you can see that there's a huge gap, right? The actual ground truth true value and estimates, they're very different. So you can see this one as well, very different, very different. Where is the orange one? You can see here, very different, right? So unfortunately, Q values often are not very accurate. So that is often called overestimation. Overestimation means the actual one, true values are much smaller than estimated one. So that Q values often suffer from overestimation. The reason is the last term here, last term. So we get target value using, this is actual reward, there's no problem with this side, but this term is the problem. We get future reward, future Q functions with our some dedicated network, target network, but we perform backs, right? That is from Bellman equation, but this one makes some problem in practice. So imagine we have two random variables, x1 and x2, and here the expectation of two random variable, and maximum of two random variable, that is visualizing the orange line, this orange star, and the, how about this one? So expectation of x1 and x2, that is, maximum, taking maximum with true values, right? So that is the green one. Mathematically, that is all called Jensen's inequality, and according to this inequality, this one, expectation with maximum of two random variable is always equal or larger than maximum of two expectation. So that is the problem. So here, this is this one. So our last term is always equal or larger than true value. That makes it, that is the problem mathematically. And this one target is not perfect, it looks noisy. And that is the reason why this kind of last term, maximum A prime Q theta bar S prime A prime overestimates X value. It always predicts larger than true value. In optimal setting, it might estimate very close to the target value, true value, but in practice, it often overestimates the next one. Here, the tricky thing is that here, max A prime Q theta bar S prime A prime. We can rewrite this one because state is state is already decided, right? State already decided, and then max A prime can be plugged into here, right? So the tricky thing is that value, Q value is also from Q theta bar, right? This one, right? But the action selected according to Q theta bar as well. So here, right? That is the tricky thing. So the last term in Bellman equation is the problem. Let's rewrite this one. We can plug in action into this one argmax. But the problem is that Q value itself is also from Q theta bar, and action to get some value that maximize Q theta bar is also from this one, triangle, right? That is the thing that we need to check to address this kind of overestimation in Q learning. This inequality is still the same as the previous one here. That is the fundamental problem. Value, action are from the same network. If the noise in this is decorrelated, then problem goes away. But the problem is that theta bar, the same network are used to get value and action at the same time, so that they are correlated, right? They are not decorrelated, they are correlated. So we need to make this one and this one, the circle one and triangle one, decorrelated by making them separate network. So idea is don't use the same network to choose action and valuation value. The idea is that is called double Q learning. Double means we introduce a additional network so that we make two network, right? We use two network to decide the this one next value. Future Q value. We use two networks to decide this value in Bellman equation. That is called double Q learning. So here, double Q learning, we use two networks. It's straightforward, right? QA, we can use here, QB and QA. Here, QA and QB. So if two Q networks are noisy in different ways, if they are decorrelated, then there is no problem. That is the philosophy of double Q learning. So we use in the Bellman, according to the Bellman equation, we need to get this one. But the problem is that value action are from the same Q theta bar, although we make it a network with a dedicated separate target network, Q theta bar, which is different from Q theta. But still, it suffers from this kind of limitation. Value and action are from the same network, so we try to make we use different network to get value and action. That is the philosophy of double Q learning. Right? So in theory, we actually need three network. In theory, right? Theta A, theta B, right? In theory, we need three network. That is too complicated. So people in practice just use theta Q instead of introducing additional one. Double Q learning in practice. So where we get two Q functions, but then just use the current target network. That is the what people do in practice. The standard Q learning is y equals to r plus gamma q theta bar and theta bar, right? But double Q learning, theta bar and theta, just use theta. So we use Q theta to get action while actual value is from Q value bar. So that is what people do in practice. Just use current network, not target network, to estimate action. Still use target network to evaluate value, right? That is what people do in practice. So without this, we actually, in theory, we need to we use three network, but just use, so originally we need to use this one, but theta A, theta, just we use this one. So we can use only two network. So there's no big difference. The difference is that when getting future value, this one, when getting action, then we just use current network instead of fixed target network. That becomes difference from standard Q learning. And so the double Q learning can be seen like this one. What target is from, value is from Q theta bar, but the action is from theta, right? We can also mathematically rewrite this one like this. So the value is from this one, Q theta bar, where action is from theta, right? We can mathematically rewrite this one. Value is from Q theta bar, where action is from theta. Actually, action can be anything. We will learn this after midterm, but you can ignore this one. I mean, at this moment, we will learn this after midterm. I mean, actually, the action could be anything, including another actor. But in double Q learning, you can know that actual value is from fixed target network, while action is from current network. Of course, we can maybe introduce, I mean, 3 network like theta 1, theta 2, where we can, so here, we can take a minimum of, here, this is not J, this is I. We can take a minimum of Q theta 1 bar and Q theta bar 2, right? Where action is still from theta. So we can make an ensemble of 2 target network by using this clipped double Q learning. That's common with Q learning, but very often used with Q function actor critique. We will learn actor critique after midterm. Right, so the philosophy of this kind of double Q learning is that we use different network for getting value and action, and in practice, people use current network to get action and target network, fixed target network to get value. And these are some practical tips for Q learning, which can be applicable to your assignments. As I said, this kind of thing is very unstable in nature, by nature, inherently. Because the target, different from supervised learning, target is not given, so that target is from its own network. Although we can do many treatment to stabilize the training. Anyway, training could be very unstable. So you need to be aware of that. Q learning takes some care to stabilize. So you need to first test on easy, reliable test first. Make sure your implementation is correct. And large replay buffer helps improve stability. It's more fitted Q iteration. It takes time. Might be no better than random for a while. Start with high exploration, epsilon, and gradually reduce. So in epsilon gradient approach, you do not need to trust your Q function at the early stage of training, because the early stage of training, your Q network will produce just a garbage value. So you should not take a greedy action at the early training stage. You just perform random action, take random action, and gradually reduce epsilon so that you can just choose the epsilon greedy approach. And the gradient can be big, so you can click gradient or use Habermas. Habermas is a combination of L1 and L2. And double Q learning helps a lot in practice, actually. There's no downside. It's always good to introduce double Q learning in practice. But n-step returns. N-step return, we learned this one, right? Instead of taking action only once, we take action n times. Then we can make our training data with longer sequences. And then we can compute the target with the more longer sequences. That is the philosophy of n-step returns. N-step returns, as I said, it has some limitations, because if we increase n too large, if we make n too large, then it will suffer from noisy, non-optimal transition between states, because action is not from optimal policy network. And schedule exploration, you can set high to low, as I said, and learning rate high to low. Atom optimizer can be helpful. And run multiple random seeds is very inconsistent between runs. So you need to be aware that this kind of RL experiment could be very different from typical supervised learning because of this kind of instability. And there are many randomness, and there are some hyperparameters you need to take care about. So you need to run multiple experiments and need to make training stable. This is the end of today, and any questions? Any question? No? Is it okay for your assignment?